Hello Math 2, this is Mrs. Bricky, and this video is for Unit 6, Lesson 4. We're going to be talking about chords. So a chord is a segment whose endpoints are on a circle. So we've got 2 points on the circle. They are connected by that red chord. Okay, our first theorem says that in the same circle or congruent circles, minor arcs are congruent if and only if their corresponding chords are congruent. So what that means is if I have a circle like this first one, if I know the chords that are marked congruent are congruent, then I know that these two arcs are congruent. So if one of them is 80 degrees, the other one is 80 degrees. And then it also sort of works backwards if I have these two arcs that are each 96 degrees, I know this chord is equal to this chord. So let's see how this works in some problems. If the measure of arc BC is 92 degrees, what is the measure of arc CD? So our goal is to figure out this arc right here. Well, in this diagram, I have two chords that are both length 8. So that means this one and this one are congruent to each other because they're both 8 units long. Well, that means whatever this is the same. And I wrote x's. You don't necessarily need to write x's. I just want to kind of show those two have the same measure. So to figure out the length, or sorry, not the length, to figure out the measure of arc CD, we're going to start with the fact that an entire circle is 360 degrees. We're going to subtract the arc that is 92 degrees. That leaves us with 268. And now we can see that the rest of the circle is broken into these two arcs that are equal to each other. So our answer will be 268 divided by 2. So that's 134. And that's our answer for the arc measure of arc CD. That's 134. This one would also be 134, and those three arcs added together add up to 360. Okay, our next theorem is if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. So this theorem, I'm going to kind of demonstrate it over here. If we have, if we have a diameter and then we have a chord, so I've got this chord that is perpendicular to the diameter, what it means is that this piece of the chord and this piece of the chord are equal to each other. And then also, we know that this arc is equal to this arc. So from here over to here is the same from here to here. And so that's always the case if the chord is perpendicular to the diameter. So anytime that makes a 90 degree with the diameter, we know that it's that the diameter is cutting that chord into two equal pieces, and that the arcs are also equal on each side of that circle. This makes sense that it has to be 90 degrees if you think about it. If I have a chord that is not at 90 degrees to the diameter, you can see that this arc and this arc are definitely not the same, right? They're definitely different. But anytime it's a 90 degree angle, we know that they are the same. So this one would be equal to this one. All right, so let's try it in an example. We've got arc BC that is 75 degrees, and we want to know the measure of arc BAD. So our goal is to find this major arc from B to A to D. Well, we have a diameter AC, and we have a chord that is perpendicular to the diameter. So that means this arc and this arc are the same. So if this one BC is 75, then CD would also be 75 degrees. Well, arc BAD is everything else in the circle, so we can get our answer by doing 360 minus 75 minus 75. and that is 210 degrees. So the measure of arc BAD is 210 degrees. Okay, so if one chord, here's our next theorem, if one chord is a perpendicular bisector of another chord, then that first chord has to be a diameter. So we know that these two chords are perpendicular to each other. If one of them is cut in half, the other one is a diameter. It has to be a 90-degree angle for this to be true. So you can see on this diagram I have to the right, if it's not a 90-degree angle, so this is not a 90-degree angle right here. If it's not a 90-degree angle, it's definitely not a diameter of the circle. And I'm going to drag this diameter over. You can see that if it was a 90-degree angle right there, so I've got that little 90 marked, it goes right through the center. Okay, so we've got our example 3 here. Find the measure of each arc in the diagram. And so we need to find these 3 arcs. Well, we have a perpendicular bisector. So the chord from A to C is cut in half, and BD is perpendicular to AC. So that means that BD is a diameter of the circle. It goes through the center. So since it's going through the center, we know that this arc and this arc are the same. So we also have a 52-degree arc here. And we know that diameter is cutting the circle in half. So we've got 180 degrees from B to D. So to get from C to D, we can do 180 minus 52. So 180 minus 52 is 128. So we've got 128 here. And again, because that's a diameter and a perpendicular chord, we know that this one will also be 128. All right. I think this is our last theorem. In the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. So what that's saying is that if we have these little distances to the center measured at 90-degree angles, if those two are the same, if they're the same distance, then we know the two chords are equal to each other. And vice versa. If we know the two chords are equal to each other, we know those distances to the center are equal. Because we know that this chord from C to D is congruent to the chord from A to B, we also know this arc and this arc are congruent to each other. So arc AB is congruent to arc CD. All right, so our example 4 here says find the measure of arc AB. Well, we know that these two chords are equidistant from the center, so we know that chord CD and chord AB are equal to each other. That means arc CD and arc AB are equal to each other. So we know the whole circle is 360 degrees, so we can subtract the two known arcs. That gives us 220 degrees, and we have two equal pieces left. So we're going to divide by 2 to get 110 degrees. So each of these is 110 degrees. So we found the measure of AB. It is 110 degrees. All right, so those are our 4 theorems. We're going to now go through sort of some mixed practice where we may need to use any one of those theorems to figure out these next 4 or 5 examples. So example 5 says find the length of RS. So our ultimate goal is to figure out how long it is from R to S. Well, we have a diameter here. It's going through the center, so this is a diameter. And this is a 90-degree angle right here. So if we have a diameter that is perpendicular to a chord, it cuts that chord in half. So we know these two pieces are equal to each other. So we can write that in an equation. X plus 4 is equal to 3x minus 12. So if we solve for x, let's see, I'm going to subtract x from both sides, and I'm going to add 12 to both sides. So when we do that, we get 16 is equal to 2x, so that means x is 8. Well, we're trying to find the whole length of RS. So if we sub in an 8 for x, we find that this is 12, and then this is also 12 because they're the same. So the length of RS, that chord, is 24. Okay, example 6 says find the measure of angle BCD. BCD. DBC. DBC. We're looking for this angle right here. All right, well, we've got markings that say that these two chords are equal to each other. If the chords are equal to each other, that means the arcs are equal to each other as well. So this one is also 107. So we can figure out this arc from C to D by doing 360 minus 107 minus 107. That's 146. So that's this arc right here. Our goal is to figure out the angle right here. Well, that angle intercepts a 146-degree arc. So if we divide that by 2, we will have our angle, which is 73 degrees. All right, example 7. The circle below is centered at point F. What is the measure of arc AE, which I have shown in kind of greenish blue there? All right, so we've got a diameter. So DB is a diameter of the circle, and we have a chord that is perpendicular to the diameter. So since that's a 90-degree angle, that means that the chord and the arc are each cut in half. So we have an equation we can set up here. We know that 4x is equal to 65 minus x. So we can solve for x. I'm going to add x to both sides. That gives me 5x is equal to 65. And when I divide by 5, I get 13 for x. So that's my x value. Well, now that I know x, I can calculate the actual value of those arcs. So since this is 4 times x, that would be 4 times 13. So this arc up here is 52 degrees. 65 minus 13 is also 52 degrees. Those two are the same, remember? And I'm going to use this central angle right here to help me. So this is a 52-degree arc. That means this is a 52-degree central angle. And there's a lot of ways you could get to your answer, but I'm going to go this way. So I know this vertical angle is also 52 degrees, which means this arc is 52 degrees. So we know the arc here and the arc on that opposite side are the same because they have vertical angle between them, centered right at the origin, right at the center of the circle. All right, well, our goal is to get the arc from A to E. Well, that's a diameter cutting that circle in half right down the middle. So to get from A to E, to get the arc AE, we can do 180 minus 52 minus 52. So that arc from A to E is 76 degrees. All right, so next example, we have a chord BD has a length of 12, and we want to know the radius of the circle. So we have this chord has a length of 12, and this little perpendicular right here, it cuts that right in half. So we've got 6 and 6. our goal is to figure out the radius of the circle. I'm going to draw it right here. It's kind of not very straight. It's like a wavy radius. Well, that radius creates is the hypotenuse of a little right triangle right there. So we can actually use the Pythagorean theorem here to figure out that length of the radius. So Pythagorean theorem says leg squared plus other leg squared is equal to the hypotenuse squared, the hypotenuse in this case being the radius of the circle. So 3 squared plus 6 squared is equal to 45. And so now if I square root to get my answer, I end up with 3 root 5 is the radius. We don't use plus or minus symbol here because we're talking about the length of the radius of the circle, so that is going to be a positive value. And so we have our answer, 3 root 5 is our radius. Okay, this next example this example 8 was kind of trying to prepare us for the next example. This is a common type of question in circles where it'll tell you a little bit about the radius and a little bit about a chord, and it'll ask you to find how far away it is from the center. Or maybe it will tell you how far away from the center it is and ask you for the length of the chord. So I've got a little list of procedures to follow on the side to help you. We definitely want to use creating a diagram to help us here. So the first thing we want to do is draw the chord. And I always just like to put the chord kind of at the bottom of the circle. We don't necessarily need our drawing to be to scale, so you don't need to stress out about are you drawing it too close to the center or too far away from the center, because our diagram is not going to necessarily be to scale. So I just like to draw my chord, just somewhere near the bottom. I prefer that versus like on the side or on the top, but you can draw it anywhere really. You're going to connect the center to the end of the chord. So basically we're adding a radius to the diagram from the center to the end of the chord. And now we're going to draw a segment connecting the chord midpoint to the center. So this is the midpoint of the chord to the center, and that's going to be at a 90-degree angle. Really good 90. Okay, so let's read through our, so you can kind of draw the diagram before you even read the question if you want, because our diagram is always going to look roughly the same. So now let's read our prompt and see if we can fill in the information on the diagram and then finish solving. In a circle of radius 10, so this is 10, the radius of the circle, how far away from the center, so this is our question that we're trying to answer, so I'm going to call this X, will a chord of length 10 be? So my chord has a total length of 10. And so since this is the midpoint of that, it's going to divide it into 5 and 5. All right, so that 5 is one of the legs of our right triangle. So now we're going to use Pythagorean theorem. Leg squared plus other leg squared is equal to the hypotenuse squared. We do a little subtraction. 100 squared minus 5 squared is 75. Make sure you do 10 squared minus 5 squared and that you don't just do 10 minus 5 because it's 10 squared minus 5 squared. So don't do an error with your exponents there. So we've got x squared is equal to 75. We can now square root both sides of our equation and we get 5 root 3. And so that is the distance to the center. So this distance right here is 5 root 3. Sometimes it helps to think about the decimal value of that just to see if it's logical. 5.3 is roughly 8.7. So this is kind of a tall sort of narrow triangle. In my diagram, it almost looks like it's an isosceles triangle, but it is not. So follow-up question, are there any angles and arcs in this circle that you might know? And I was kind of hoping you would notice that this is one of our special triangles. If it's 5, the hypotenuse is 10, and this height is 5 root 3. This one's a little more drawn to scale. This is a 60-degree angle and a 30-degree angle. So if we have a 60-degree angle and a 30-degree angle, we can find some arcs and things. So first of all, we know that this is a 30-degree arc and this is a 30-degree arc. And if we drew this line connecting that to a diameter, from that radius to a diameter, we know that this is a 120-degree arc. So there's several things we could find knowing that that's a special right triangle. All right, example 10, I just wanted to try one more similar problem because it is a little bit tricky. So we're gonna, again, follow these procedures. Draw your chord first. Connect the center to the end of the chord, creating a radius there, and then connect the midpoint of the chord to the center, and that will be at a 90-degree angle. So this one says if a chord is 5 inches from the center, so we know this distance is 5. The circle has a diameter of 14 inches. That means the radius is 7. Our question is, how long is the chord? So we really are looking for this whole distance. Well, I'm going to call this part of it, the part that's the leg of the right triangle, I'm going to call that x. And then the pink would be to double that. And that's our ultimate question, is what is the 2x? All right, so for our right triangle, using Pythagorean theorem, x squared plus 5 squared is equal to 7 squared. We're going to subtract the 5 squared from both sides to get 24. And now we can apply the square root to get 2 root 6. So that would be just the x. That's just the green part, the leg of the triangle. So to get the whole length of the chord, we need to double it. So the chord would be 4 root 6. Okay, that is it for our lesson on chords. If you have any questions, let me or your math teacher know. Thanks.